Okay, in this class I am going to talk about the IR and Raman active vibrations in square planar AB4 type of molecules. IR and Raman active vibrations in square planar molecules. Okay, we have already seen the hybridization of this type of molecules, that is square planar AB4 type of molecules, and there we have already seen the character table for this type of molecules, right? Square planar molecule. So let me draw the square planar molecule here, AB4 type. So let me draw a square, okay, and in the midpoint of the square we have the A atom. This is A, and the B atoms are placed at the corners of the square. Okay, so this constitutes the AB4. So you can see the bonds here. So this is how the AB4 type of molecules are there. And this is a square planar molecule. And what are the symmetry elements you can see in this square planar molecule? You can see the C4 axis here, right? C4 axis. And the C4 axis is perpendicular to the plane of the molecule. And it is passing through the central atom, A. So this is C4 axis. Okay. So let me write the symmetry elements that you can see here. And these are that is C4, C4. So how many C4 are there? C4 is there, C4 square and C4 cube. But a C4 square we cannot regard like that because this is equivalent to C2. This is equivalent to Z2. So we have to write the C4, C4 cube, then C2. Then we have C2 dash or C2 prime. This is this axis, okay? C2 prime axis is this one. That is the axis which is passing through two of the opposite AB bonds, okay? So this is a C2 axis, okay? How many C2 axes are there like that? Two C2 axes are there like that. This is also a C2 dash, C2 dash, okay? These are C2 dash axis. So there are two C2 dash, and then there is a C2 axis that is bisecting the BAB bonds. Okay, so this is C2 double prime, and there is another axis like that. That is also C2 double prime axis. Okay, so there are two C2 double prime axis, and there is an inversion center because the center of the molecule is the inversion center. This A is an inversion center. Inversion center is there. Then S4 is there because C4 axis coincides with the axis S4 axis itself. But there is a difference in the operation. In the case of C4, we are rotating the molecule by 90 degree. That's all. But in the case of S4, we are rotating the molecule by 90 degree, and then after that we will make a air reflection. But in the case of C4 and S4, the axes are coinciding or axes are same. Okay, so we have S4 also, and S4 is there, and S4 square. S4 square is not there because S4 square also S4 square. S4 square is what is S4 square? S4 is C4 followed by sigma h, right? C4 followed by sigma h in this case. So square of this one, it means that sigma h square C4 square. That is sigma h square is nothing but E, and C4 square is C2. So this is equivalent to C2. Therefore, we cannot write C4 square because S4 square, because S4 square is equivalent to C2. Okay. Then S4 cube is there. S4 cube is there. So that is a unique operation. And S4 raised to 4 is not there because S4 raised to 4 is equal to E. Okay, so that we cannot write. So how many S4s are there? S4 is there, S4 cube is there. Okay, so there are two S4s total. And there is a sigma h. Sigma h is this plane, that is a molecular plane is a sigma h plane. And then there are sigma v vertical planes. Okay, these vertical planes are perpendicular to the molecular plane, and at the same time they contain the AB bond, two opposite AB bonds. So the vertical planes here, the sigma v planes, are perpendicular to the plane of the molecule, and at the same time it contains the C2 dash axis. Okay, so there are two of these kinds of vertical planes. One is through here and another vertical plane is through here. Okay, so these are vertical planes, 2 sigma v. Okay, so sigma v passes through, sigma v contains C2 dash axis also. And in addition to that, there are two other vertical planes. They are actually dihedral planes because they are bisecting the BAB bonds. And these vertical planes are containing the C2 double prime axis. So there will be one vertical plane through here. It will contain the principal axis as well as the C2 double prime axis. Okay. So that's a vertical plane. But since it is bisecting the bond angle, then it can be called as a dihedral plane. So there are how many dihedral plane like that, or sigma d's like that? Two sigma d's are there. Okay, one through this C2 double prime axis and another through this C2 prime double prime axis. So there are two sigma d's. So these are the symmetry elements that we can see in the case of AB4 type of molecules. Okay. And now with this information, we have the character table already. I have given the character table here. Okay, you can see that E2C4, C2, C2 prime, 2C2 prime, 2C2 double prime, I, 2S4, sigma H, 2 sigma V, 2 sigma D. Okay, these are the elements that we can find in the character table. So how many elements are there in total? 1 plus 2, 3 plus 1, 4, 4 plus 2, 6, 6 plus 2, 8, 9, 11, 12, 14, 16. 16 elements are there in this point group. Okay, 16 elements. So order of the group H is equal to 16. Okay, and it belongs to D4H point group. D4H point group. So these are the basic informations that we have to have before assigning before getting into the vibrations or the Raman active and here active vibrations. Okay, with this basic information, I am going to calculate the total character corresponding to the 3n degrees of freedom. We have done this in the previous cases as well. For the case of water molecule and also in the case of ammonia, we have done this. So you actually know the procedure for doing this. So let me do this. Okay, I am going to construct the I'm going to calculate the total character corresponding to 3n degrees of freedom. Okay, so let me write the elements here for D4H. So this is a D4H. Okay. The elements are E, then C2C4, 2C4, then C2, okay, then 2C2 prime, 2C2 prime, then 2C2 double prime, okay, and after that inversion I, then S4, 2S4 are there, 2S4, then sigma H, okay, then 2 sigma V, 2 sigma V, and 2 sigma D, okay. So I am going to calculate the total character corresponding to 3n degrees of freedom. Before that, we have to classify all these operations as either the proper rotations or the improper rotations. We already know that E and proper rotations C4, C2 and C2 dash, C2 double dash. Okay, these are regarded as the proper rotations. So let me draw a dotted line here, and this dotted line will separate the proper rotations from the improper rotations. And we can consider I, inversion center, okay, that as an improper rotation, okay, and this one means I is nothing but S2, and this one already is an improper rotation. Sigma H, sigma V, sigma D, these are reflections. These can also be considered as improper rotations because the sigma operations can be considered as S0, okay, S0. So with this information, I am going to calculate. So theta for each of these I will assign. What is the theta corresponding to identity operation? that is 0. Identity operation is nothing but C0. So theta is equal to 0. And in the case of C4, theta is equal to 90. In the case of C2, it is 180. And in the case of this C2, it is 180. In the case of this C2, it is 180. And in the case of I is nothing but S2. Since it is S2, it is again 180. And S4, 90. For sigma h, it can be considered as S0. Therefore, theta is equal to 0. This is also 0. This is also 0. So cos theta is cos 0 1 and cos 90 is 0, cos 180 minus 1, so minus 1, here also minus 1, and cos 90 0, then cos 0 1, 1, 1. Okay, so these are the cos theta values. And now we have to obtain the plus or minus 1 plus 2 cos theta. For that, I am going to write 2 cos theta also here. 2 cos theta is equal to 2, 0, minus 2, minus 2, minus 2, minus 2, 0, 2, 2, and 2. These are 2 cos theta. Now I am going to calculate plus or minus 1 plus 2 cos theta. Okay. We will apply plus 1 in the case of proper rotations, that is the operations left to the dotted line, and we will apply minus 1 to those operations which are right to the dotted line, that is improper rotations. Okay, so in all these cases we have to apply plus 1. So 2 plus 1 3, 0 plus 1 1, minus 2 plus 1, that is equal to minus 1, minus 2 plus 1 minus 1, minus 1 here. And here we have to apply minus 1. So minus 2 minus 1 is minus 3, and 0 minus 1, that is equal to minus 1. 2 minus 1 1, so it is 1 1. Okay, so now we have plus or minus 1 plus 2 cos theta, and now we have to assign NR. NR is the number of atoms retaining positions during each operation, right? Number of atoms retaining position during each operation. So we know that during E operation, none of the atoms are changing their position. Therefore, NR in this case is 5, right? Because total number of atoms is equal to 5 in AB4. And in the case of C4 rotation. So C4 rotation is the rotation about this axis, and that axis is passing through A, right? So only one atom is lying in the symmetry element. Therefore, that atom will retain its position. All other atoms will change their positions. Therefore, NR in the case of C4 is equal to 1. Okay. And what about C2? In the case of C2, we have C2 is nothing but the C4 axis itself. Okay. C2 in this case is nothing but the C4 axis itself. And therefore, during the C2 rotation, only A will retain their position. All other atoms will change their position. So, in the case of C2 also, the number of atoms retaining NR is equal to 1. But what about C2 prime? C2 prime is this axis. This is a C2 prime axis. And C2 prime axis contains 3 atoms. B, A, B. 3 atoms are there. So these 3 atoms will retain their position. Other atoms will change their position. So NR in the case of C2 prime is equal to 3. Okay. And what about C2 double prime? C2 double prime is this axis, and that axis contains only one atom, that is the central atom A. So that only will retain the position. Therefore, NR is equal to 1. Okay, NR is equal to 1. And what about inversion? And inversion center is nothing but the central atom only. Okay, so central atom lies in the inversion center, and therefore during the inversion, central atom will retain its position. All other atoms will change their position. Therefore, in the case of inversion, NR is equal to 1. And what about S4? S4 axis is coinciding with the C4 axis. See, this is S4 axis itself. S4 and the C4 are coinciding. Okay, so if the S4 contains only one atom, that is A, therefore for S4 also the number of atoms retaining position is equal to 1. Okay, and what about sigma h? Sigma h is the molecular plane. Molecular plane is the sigma h, and the molecular plane contains all the elements AB4. Okay, all the elements are there in the molecular plane. Therefore, all the 5 elements, or all the 5 atoms, not elements, all the 5 atoms retains their position during the sigma h. So it is 5 here. Okay, and what about sigma v? Sigma v. the vertical plane sigma v. See, sigma v is passing through here. Okay, so the sigma v contains B, A, and B. So three atoms are there in the sigma v plane. So those atoms will retain their position. So Nr in the case of sigma v is equal to 3. And what about sigma d? Sigma d is the dihedral plane. It is passing through here. Okay, it is bisecting the BAB bond angle. So this sigma v double prime, no, not sigma v, sigma d. Okay, sigma d, the dihedral plane, contains only one atom, that is a central atom. Therefore, that only will retain the position, and therefore Nr in that case is equal to 1. Okay. So now I can find out Nr into plus or minus 1 plus 2 cos theta. Nr times plus or minus 1 plus 2 cos theta. Okay, 2 cos theta. That is 5 into 3, that is equal to 15. 1 into 1, 1. 1 into 1 minus 1. So this is minus 3. Again minus 1. Then minus 3. Then minus 1. Then 5. Then 3 and 1. Okay. So we have the total character set. That is, this total character set corresponds to 3n degrees of freedom. So the total character set corresponding to 3n degrees of freedom is 15, 1, then minus 1, then minus 3, then minus 1, then minus 3, then minus 1, then 5, then 3 and 1. Okay, this is the total character set corresponding to 3n degrees of freedom. Total character set corresponding to 3n degrees of freedom. And now, let me now calculate the total character set corresponds to the translational degrees of freedom, and a total character set corresponding to the vibrational degrees of freedom. Okay, and for that we can do very easily for the rotation degrees of freedom. So translation and rotational can be easily picked out from the character table. So we look at the character table and pick out the degrees of freedom corresponding to translational and the rotational. But before that, we have to know the symmetry species corresponding to that. What we have to do for obtaining the symmetry species corresponding to that, we have to reduce this, right? This is the total character set corresponding to a reducible representation, and we have to reduce it, and we have to find what are the contributions of the reducible representations from the character table towards this total character set, and that we can do by applying reduction formula, right? So let us apply the reduction formula here. Reduction formula. And you know that this is corresponding to E. Let me write it here. This corresponds to E. This corresponds to E. This is for C4 to C4. Then this corresponds to C2. This is for C2 prime. This is corresponding to C2 double prime. This corresponds to I. Then this one corresponds to 2S4. Okay, this one corresponds to sigma H, this one to 2 sigma V, and this one for 2 sigma D. Okay, so I am going to reduce this. Okay, and what are the reducible representations that you can find in the character table? A1G first. So let me take A1G, and I am going to find out the total character corresponding to the number of times A1G will appear. Okay, N A1G. So A1G is the totally symmetric representation, 1 1 1 1 1 1. Okay, so I can easily do this. So N A1G is equal to 1 divided by 16, that is 1 by H order. Okay, 1 by 16 into 15. Okay, plus 2 into 1, that is equal to 2. Actually 2 into 1 into 1, that the final one comes from the character table, okay, corresponding to A1G. Since it is 1, that is not going to make any effect. That is why I am not saying it every time. So 1 into 15, 15 plus 2 into 1 is equal to 2. plus minus 1. So let me write minus 1 here. Minus 1. Then minus 6. Then minus 2. Then minus 3. Then minus 2. Then 5. Okay. Plus 6 plus 2. Okay. That is equal to 1 divided by 16. 1 divided by 16 into 15, 17. The 17 minus 1, that is 16. 16 minus 6, that is 10. 10 minus 2, 8. 8 minus 3, that is 5. 5 minus 2, that is 3. 3 plus 5. 3 plus 5 is equal to 8. 8 plus 6, 14. 14 plus 2, 16. So this is 16. So 16 by 16 is equal to 1. Okay. So n A1G is equal to 1. And like that, you can now find out Na2G also. Na2G. Na2G is equal to 1 divided by 16 into, okay. So we have to see the characters corresponding to A2G. So the characters corresponding to A2G are 1, 1, 1, minus 1, minus 1, 1, 1, 1, minus 1, minus 1. Okay. So let me put it there so that you can see better. This is A2G. Okay, so this one corresponds to A2G. Let it be here for the time being. So this is 111. Then it is we can write 15 plus 2. Then minus 1. Then comes minus 1. So this is plus 6. Then minus 1. That is plus 2. Then 1. Okay. So it is minus 3. Then minus 2. Okay, then again plus 5, then minus 1. So it is minus 6. Then minus 1. So it is minus 2. Okay, so that is equal to 15 plus 2, 17. 16. 16 plus 6, that is 22. 24. 24 minus 3, 21. 21 minus 2, that is 19. 19 plus 5, that is 24. 24 minus 6, that is equal to that is equal to 60, right? 24 minus 6, that is equal to 18. Okay, 18 minus 2, that is equal to 16. Okay, so 16 by 16, 16 by 16, that is equal to 1. Okay, so Na2G is also equal to 1. Na2G is also equal to 1. And okay, now I have to find out for next the character set, that is for B1G. Okay, so NB1G, B1G, that is equal to, you can find out in the same way, and you will see that NB1G is equal to 1. Okay, and you can find that NB2G, NB2G is also equal to 1. Okay, and then we will see that NEG is also equal to 1. Then you will see that Na2U is also equal to 2, and then you will find that NB2U is equal to 1, and EU is equal to 3. Okay, you can follow the same procedure for all these. Okay, and now we have reduced the total character set, and we have seen the weight of the irreducible representations contributing to this total character set. Okay, and based on this, I can write total character set corresponding to 3n degrees of freedom. 3n degrees of freedom. Total character set corresponding to 3n degrees of freedom. 3n. That is equal to A1G plus A2G plus B1G okay, B1G plus B2G plus EG plus A2U plus B2U plus 3EU. Okay, so this is how I can represent the total character set corresponding to 3n degrees of freedom. Now I can take the symmetry species corresponding to translation degrees of freedom. That I can do directly from the character table. So let me take the character table here, and I will check which are the symmetry species belonging to X, Y, and Z. Okay. So corresponding to Z we have A to U, and corresponding to X and Y together we have EU. So we have to write A to U plus EU. Okay, A to U plus EU. So translational A to U plus EU. Okay, A to U plus EU. A to U plus EU. And I said, looking at X and Y, you should not write 2EU because X and Y together transforms as EU, and EU actually is a doubly degenerate representation. Therefore, you need to write it only one time. It indicates that X and Y together transforms as EU, and for X and Y together, you need to write EU only one time. Okay, don't write 2 times EU. Okay, it is only one time EU. See, these two are inside the bracket. It means that they are transforming together. They are not independent. Okay, they are dependent variables. X depends on Y and Y depends on X. Therefore, together for X and Y, you need to write EU one time. That's enough. Okay, don't make mistake by writing 2 EU. Okay, so you need to write only EU. And now I am going to pick those for rotational. That can also be done from character table. So you look for Rx, Ry, and Rz. Alright, Rz corresponds to A to G. Okay, and Rx and Ry, they transforms together, and they are transforming as Eg. So what we have to write? A to G plus Eg. A to G plus Eg. So A to G is here. A to G plus Eg plus Eg. Okay, so these are the ones corresponding to translational and rotational, and we can directly pick from the character table. And now we have to subtract the one for translational and rotational from the total degrees of freedom, the total character corresponding to the 3n degrees of freedom. So what will be the result when we are subtracting 3n minus translational minus rotational? Okay, so that corresponds to the vibrational degrees of freedom. So the total character set corresponding to vibrational degrees of freedom, that is equal to A1G, that is coming from here. Then A2G minus A2G, then there is no A2G remaining. Then B1G, okay, let me write plus B1G here. B1G is there plus B1G. Then B2G is also there plus B2G. But what about EG? No, EG is not there. EG minus EG. So no EG is remaining. Then A2U, B2 A2U minus A2U. So there is one A2U plus A2U plus B2U plus 3EU minus EU plus means remaining is 2EU. Okay, these are the total character set corresponding to vibrational degrees of freedom, or these are the symmetry species contributing to the total character corresponding to the vibration degrees of freedom. A1G contribute one time, B1G contribute one time, B2G contribute one time, A2U contribute one time, V2U contribute one time, and EU contribute 2 times. Okay, so the symmetry species, the symmetry of the normal modes of vibrations, the symmetry of the normal modes of vibration in the case of the AB4 type of molecule is A2G plus B1G plus B2G plus A2U plus B2U plus TU. TU. Okay, let me write it here once again. That is this one. Okay, it is here. Okay, so this is corresponding to the vibrations, different vibrations. Okay, so um, let me now assign which one will be Raman active and which one will be IR active. Okay, A1G. What about A1G? What about A1G? A1G is Raman active or not? A1G. You can look at the character table. We will check first check IR active. Okay, so in order to see whether it is IR active or not, you have to check whether there is X, Y or Z coordinate corresponding to A1G. Is there any X, Y, Z coordinate corresponding to A1G? No. Only binary products are there. Okay, so A1G is not IR active. So we will write inactive. For IR, we will write it inactive. IR. This one is for IR. This A1G is IR inactive. 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 Okay. And what about B1G? B1G. B1G has any XYZ? No, there is no XYZ corresponding to B1G also. That is also IR inactive. So let me write IR inactive. Inactive. What about B2G? B2G. Corresponding to B2G, is there any XYZ? No, there is no XYZ, only binary products are there. So B2G is also IR inactive. So let me write it there, inactive. B2G is also inactive. Okay. And what about A2U? Is there any XYZ coordinate corresponding to A2U? This one? Yes, there is Z. So that is IR active. Since there is Z, A2U. Okay, A2U corresponds to Z, so that is IR active. So let me write IR active here. So A2U is IR active. And what about B2U? In the case of B2U, is there any XYZ ones? No, there is no XYZ, there is no binary products as well. So that is also IR inactive. Okay, that is IR inactive. So this is inactive. And the last one, there are two EU. Okay, what about EU? Is there any XYZ? Corresponding? Yes, there is X and Y. So that is active. Okay, so let me write IR active. Active. So how many IR active lines are there? This A2U is IR active. Then there are two EUs. Both of them are IR active. All other symmetries are belonging to IR inactive ones, right? And now we are looking for the Raman. Raman. So let me take another color for that, for Raman. Raman. We will check the Raman activity. Or A1G. In the case of A1G, is it Raman active? Yes. Binary products are there. Therefore, we can write it is Raman active. So it is active. What about B1G? B1G. B1G we can check, is there any binary product? Yes, there is a linear combination of the binary products. That is also fine. X square minus Y square is the linear combination of binary products. So B1G is also a Raman active. Okay, so this one is a Raman active. Raman active. And what about B2G? B2G. We will check B2G. B2G is here. Is there any binary product? XY is there. That is XY. That is binary product. So B2G can also be taken as Raman active. So let me write Raman active here. Active. And what about A2U? A2U. A2U. Okay. A2U is here. A2U. There is no binary product corresponding to A2U. Therefore, it is Raman inactive. Raman inactive. This is inactive. Okay. Raman inactive. And what about B2U? B2U. B2U is here. Is there any one? No. It is. There is no binary product. Therefore, it is Raman inactive. Okay. Raman inactive. Inactive. And what about the last? EU. EU. EU has any binary product corresponding to that? No. Therefore, it is Raman inactive. Raman inactive. This is inactive. Okay. So here you can see that A1G is IR inactive but Raman active. Okay. B1G is IR inactive but Raman active. B2G is IR inactive but Raman active. A2G is IR active but Raman inactive. And B2 is IR inactive and Raman inactive. Okay, this one is both IR inactive and Raman inactive. B2U, IR inactive and Raman inactive. And the other one, EU, it is IR active but Raman inactive. And so what you can see here, whatever line you are seeing as a Raman active, these are Raman active lines, right? Raman active. Okay, all those are IR inactive. These are Raman active and they are IR inactive. And all those you see as a IR active, these are IR active. Okay, and they will be Raman inactive. Okay, of course there is one vibrational mode which is both Raman inactive and IR inactive. That's fine. But whatever you see as the Raman active will be IR inactive. And whatever you see as the IR active will be Raman inactive. Okay, what is this actually? You have seen this as the mutual exclusion principle, right? Mutual exclusion principle. So, from the mutual exclusion principle, those compounds which contain an inversion center, and for those compounds, the Raman active lines will be IR inactive, or Raman active vibrations will be IR inactive, and IR active vibrations will be Raman inactive also. But there is possibility that one particular vibration can be both Raman inactive and IR inactive. That is also possible. But if any of the vibration is Raman active, it will be definitely IR inactive and vice versa. Okay. So that is a mutual exclusion principle. So mutual exclusion principle. So the symmetry gives you a very good explanation for the mutual exclusion principle. You can see this from the symmetry. Now you have learned this mutual exclusion principle while learning the Raman spectroscopy, but now you understand why they are mutually excluded. It's because of the symmetry, right? Symmetry doesn't allow for one Raman active vibrations to be IR active or one IR active vibrations to be Raman active. The symmetry doesn't allow that. Okay, so the mutual exclusion principle is well established here also. Okay, so these are the things that you have to understand. So how many vibrations are there? How many modes of vibrations are there? That I didn't say. So you can calculate from 3n minus 6, right? This is a non-linear molecule, therefore you can use the formula 3n minus 6. So 3 into, how many atoms are there? 5. So 3 into 5 minus 6, that is 15 minus 6, that is equal to 9. Okay. So 9 vibration modes are there, and you can count these vibration modes. Okay, A1G is a vibration mode, then B1G is second one, then B2G is the third one, then A2U is the fourth one, then fifth one is B2U. B2U is the fifth one, and then there are two EUs, right? EU plus EU. And how many are there? This EU is a two-dimensional representation. It means that there are two modes in this EU. They are degenerate. Two degenerate modes are there. So there is one mode, there is one mode, there is one vibration mode, there is one vibration mode, there is one vibration mode, and there are two vibration modes, but they are degenerate. Means these two vibration modes will have the same energy. And corresponding to this EU also, there will be two vibration modes, and they will also be degenerate. So totally how many are there? 1, 2, 3, 4, 5, 7, 9. 9 vibrational modes are there. Okay, that is what you can get from this equation also. So this is what you have to understand about the AB4 type of molecule, square planar AB4 type of molecule, and this molecule belongs to D4H, and this molecule is special because it contains an inversion center, and you have seen here what are the vibrational modes and which are Raman active and which are IR active. You have established the mutual exclusion principle here, and you have seen that this vibrational modes you have calculated are well fitting with the number of vibration modes you can get from the 3n minus 6 formula. Okay, so these are the things that you have to know, and you know why these are like that. Okay, I have already explained in detail why certain modes are IR active and certain modes are inactive. I have explained the theory well in my previous lectures. So I recommend you to go to those lectures as well. Okay, I hope you enjoyed this one. I hope you have no problem with this one. So whenever you get any molecule, perhaps you may be asked to find out the IR active and Raman active vibrations in XCF4. Okay, and XCF4 is a square planar molecule. You know this already, and its symmetry is D4H. So maybe it will be asked like this XCF4. Okay, so depending upon the molecule, you must be able to assign the point group, and then you have to know the symmetry elements present in that molecule. And once you assign the point group, you can use the character table. You can use the character table to assign the symmetry species corresponding to translation rotation. Before that, you have to calculate the total character corresponding to 3n degrees of freedom. That you can do using these steps. Okay, and after that you have to use the reduction formula. From the reduction formula, you have to get the weight of each reduced representation contributing to the total character, and then you have to represent the total character like this. Out of that, which are representing the translation, that you can get from the character table, which are representing the rotation, that also you can get from the character table. Then subtract the translation and rotation from the total degrees of freedom. Okay, then you will get the symmetry species corresponding to the vibration degrees of freedom, and then you will look at the character table. Okay, character table, and assign whether these are IR active or Raman active. Okay, and special care should be given when you are assigning the Raman active and IR active vibrations. In the case of water molecule, you saw that the Raman active vibrations are IR active also. In the case of ammonia molecules also, you saw that the Raman active vibrations are IR active also. But here you cannot see that because this molecule is special. It has a inversion center. Therefore, mutual exclusion principle will work here. Automatically, you can see that mutual exclusion principle is in work. Okay, and then you have to ensure that how many vibrational modes you can see. If there are any degenerate vibrational modes, everything you have to write. Okay, so that is what you can understand from the group theory about the Raman activity and IR activity of this type of molecules. Hope you enjoyed this lecture, you understood well. If you have any doubt, please don't hesitate to ask me. Thank you for watching and stay tuned.